Hello everyone, my name is Alireza Mohebbi. I'm a registered professional engineer in structural engineering, and I'm a senior research engineer working at SES Group and Associate at Federal Highway at Turner Fairbank Highway Research Center. And I'm going to talk about UHPC creep and shrinkage. Here's a disclaimer that I do not represent the government. So my presentation has three main parts. The first part is about UHPC time-dependent properties. I'm going to talk about compressive creep and unrestrained shrinkage. I will provide some data to help the community to get the feeling about the material properties. Then I'll be talking about the creep and shrinkage model developments, the procedure that we follow to develop models. And then for the model verification, I will compare the predictive models with the full-scale testing of pretensioned UHPC girders, and I'll show girder construction. I will be focusing on pre-stress losses. The important time-dependent properties is compressive creep. Creep is a deformation of concrete under sustained load. We follow the standard ASTM C512 with some modification in ASTM C1856. We have 4 specially designed actuated loading frames, and we had a lot of experimental variables, including loading age, sustained stress level, relative humidity, and UHPC types. And we ran creep tests, like we had 3 series of creep tests, technically 3 years of data points. So in one of the experiments, let me bring my laser point. All right. I think it's shown there, right? Okay. So in the first series of, in one of the series of the creep tests, in one of the frames, we decided to create a high humidity environment. We tried to achieve 80% relative humidity. We measured that, and we kept that humidity in 1 year. And we tested the experiments at the early age when the compressive strength was 14 KSI, and the target sustained stress was at 65% of F prime sub C, which is relatively high. And this 65% is consistent with the compressive stress limit in AASHTO for design of pre-stress girders. Frame number 2 is similar as frame number 1. The only difference is the relative humidity, which is 50%. And frame number 3 is also similar as the other frames, but represents provides this samples with the sealed conditions. Those frame and those results provide represent basic creep, the creep that occurs under no moisture exchange between specimens and the environment. And the 4th frame is the similar as other frames, same UHPC class materials, but the only difference is they were loaded at 20 KSI when the specimens were mature. We call that mature age loading. So technically, the first 3 specimens, they can represent a structural member that is being loaded at the early age, like pre-stress girders, and the 4th girder represents post-tensioning, or any structural member that is loaded at the later age. Now, let's look at some results. I'm providing the results of 1 UHPC class materials, but we tested 8 different classes. So in this plot, we are looking at the mature age results and the early age results. We are looking at the creep coefficients. The creep coefficients for mature age is shown with the purple color with the triangle. And the other 3 plots in the figure, it's for early age loading. So we can see the creep coefficient of the same material loaded at the early age is much less than the early age loading. We also notice that there is a slight difference between different environmental conditions that we have, and the specimens with high humid environment shows a slightly less creep. Now, in the other plot, in the middle, we are looking at the results of 8 different UHPC class materials, and it's a logarithmic view of the plot to make some bigger picture conclusions. And the vertical axis is the creep strain. The reason that I would like to show the creep strain is I would like the community have a feeling about the amount of the deformation that the specimen, even UHPC, can go through. So these specimens were loaded at 14 KSI, and we had 2,000 on average to 4,000 macro strain. That's a good deformations. And also we had one UHPC class material that shows about 7,500 macro strain. And however, when we look at the creep coefficient, which is technically the creep strain divided by the instantaneous elastic deformation, the creep coefficient was between 0.9 and 1.5, except the one for UE, which was more. And to give you the feeling about what is the normally expected value for conventional concrete, the creep coefficient is usually between 1.5 to 3. So we can see even with the highly stressed UHPC, the creep coefficient compared to conventional concrete is much less. Now, with the same loading and same UHPC class materials, but the materials were loaded at the later edge when they had 20 KSI. The creep strain was almost half of those loaded at the early edge. So as we have a more mature specimens loaded at 20 KSI, the creep deformation is going to be much less. Now, here is an interesting plot. Technically, in this plot, I'm looking at the ultimate creep percentage. So for instance, I would like to know how long does it take for UHPC to achieve certain percentage of the ultimate creep. So for instance, we had between these 8 UHPC class materials that we had some materials that in one day it reached 50% of the ultimate creep. And also we had some other UHPCs that it took 7 days in order to reach half of the ultimate creep. So here is the important point that the majority of the creep is going to happen at the early edge, at the when the load is applied. And also another important point is sometimes we do secondary curing to cure the structural member. So secondary curing may not be even efficient for UHPC because if the majority of the creep is happen at the early edge, the material may not have the chance to develop those mechanical properties. Now, another time-dependent properties is shrinkage. Shrinkage is a deformation of concrete due to loss of moisture and hydration of cementitious materials. We followed ASTM C157 with some modifications explained in ASTM C1856. So in beginning, I should say that the results that I'm presenting for shrinkage is from time of demolding to the ultimate. So technically, the shrinkage that occurs from the set time until the demolding, we did not consider it in this research. Everything is from demolding until the ultimate. So we have several variables, relative humidity and UHPC types. We used sealed conditions. So the reason that we seal the specimen is to only look at the shrinkage that is due to the chemical reactions. So there is no moisture exchange between the sample and the environment. And we also have some specimens in the drying environment. Now let's look at the results of 8 different UHPC class materials that we tested. We are looking at the total shrinkage. Total shrinkage includes the autogenous shrinkage and the drying shrinkage. And we could have a class material that the shrinkage strain is about 300 macro strain. Also, we could have some UHPC class materials that goes until 700, 800, and even we have one which is slightly more than 1200 macro strain. So we are dealing with a material that can have a wide range of shrinkage. But when we look at, the normally expected value for conventional concrete, we can get the conclusion that even the total shrinkage of UHPC is about in a range of the normally expected value for a well-designed conventional concrete. So this is a total shrinkage, and if we deduct the results of a sealed condition from the total shrinkage, we get the drying effect. Drying effect at 50% humidity. And as we can see in the results, the drying effect is small. It includes a small portion of the total shrinkage. Now, here is another interesting plot. So in this plot, I'm looking at the autogenous shrinkage, which is the results of the sealed condition, and the total shrinkage. And with the 8 different class materials, the average, the slope of the line of best fit of these materials is 0.8. That means 80% of the total shrinkage is autogenous shrinkage. Now, here are some concluding remarks. UHPC loaded at both early age and mature age, they both exhibited the ultimate creep coefficients that is less than the normally expected value for conventional concrete. The ultimate creep coefficient for specimens that were loaded at the mature age, they were almost half of those loaded at the early age. And the drying shrinkage of UHPC is small, and the majority of the shrinkage that occur is for autogenous shrinkage, which is technically the chemical shrinkage. Shrinkage due to chemical reactions. Okay, now I'm going to talk about the procedure that we follow to develop the models. So AASHTO LRFD section 5.4 has this table, a refined method to calculate creep coefficient and strain. We look at these parameters. There are a lot of parameters. There are humidity correction factors, strength correction factors, maturity, size factor. So we evaluate each parameter, we determine the applicability of those, and if we need to update or if we could use the same equations. So here I should say we have published a lot of papers, like 3 papers, 1 conference paper, 2 journal papers. Everything that I discuss here is discussed more in details in those papers, which I'm going to show it more, but I'm going to just talk about the bigger pictures and the main conclusions that we get. So I want to quickly follow the procedures that we developed the equation, and it has been explained in the AASHTO LRFD. The first item is the equation coefficient. Technically, these are the average value of the ultimate creep or ultimate shrinkage of specimens in a baseline condition. So the baseline condition for AASHTO or conventional concrete is a humidity of 70%, volume to surface ratio of 3.5 inch, F prime sub Ci of 4 KSI, and the sustained stress 40% of the F prime sub Ci. So our baseline condition was different for UHPC because we stressed the specimens more, and the humidity, we had the majority of our data was at 50%. Volume to surface ratio was 1 inch, which is technically correlated to 4x8 cylinders. And we loaded the specimens, our baseline condition 14 KSI, and the sustained stress was 65% of the F prime sub C. So with that 8 different UHPC class materials, the average value of the ultimate creep was 1.2, and the shrinkage was 600 microstrain. The second parameter is a humidity correction factor. So we had creep specimens in different humidity, in different environmental conditions. We normalized it. We tried to develop a line of best fit, and we realized that the one that is presented in AASHTO for conventional concrete has a larger slope, and the humidity correction factor for creep is different. So we decided to update that equation. We followed a similar procedure for shrinkage. There is another factor, humidity factor for shrinkage. However, we noticed that the line of our best fit is very close to what is in the AASHTO. AASHTO is shown with the green line. So we decided to adopt the AASHTO equation. However, because our baseline condition was different, so the equations may look different because it's normalized to our 50% relative humidity. The other correction factor is a strength correction factor. Technically, it's a reduction factor that modifies the ultimate creep and shrinkage based on the compressive strengths at the time of loading. AASHTO has provided these equations. Technically, there's a concept behind it. This factor gives 1.0 for a specimen which is loaded at 4 ksi, and the compressive strength at service is 5 ksi. So I plotted here with the green curve, and as we can see, because UHPC has larger, technically it's more than 10 ksi, the compressive strength, and it's until it can go to 2 ksi, 25 ksi. So if we just use whatever that is in the AASHTO, it's going to give us a very large reduction factor. So that's not going to be, the current format is not going to be applicable. So we followed the similar thought process. We had our data, we found our best fit, and with the concept behind it that our proposed strength factor gives a factor of 1.0 when the specimen is loaded at 14 ksi and the compressive strength at service is 18 ksi. So we updated that equation. The other parameter is the size correction factor. So technically, the shape and the size of the concrete member affects the rate that moisture goes into or escape out of it. So, however, we know that UHPC has a microstructures, very dense microstructures. The pores are disconnected, and based on the results of the creep and shrinkage, we notice that there is a slight difference when we look at the sill condition that technically presents the creep at with infinity correction factor. So it's usually in the concrete there is a large slope from volume to surface ratio of 1, and it approaches to the sill condition. However, we see a small slope, but we decided for now to consider it 1.0, and however, we may have further information later, and we may update that correction factor. The other one is the the loading age correction factor. So the green one is whatever it is in the AASHTO, and we decided to slightly modify the loading age correction factor that is well represented for UHPC and fits better for based on our data. We also provided a floor of 0.5 that we don't want to go lower than this factor to apply large reduction factor to the creep prediction. For the time development correction factor, technically this is the only parameter that is a function of the time, and it defines the behavior of the creep. So we know that UHPC has a high volume of fibers, higher compressive strength, higher modular of elasticity. The mix is different, the low water to binder ratio. So the equation that is being developed for AASHTO is not going to represent for UHPC. We decided to update that one, and which is shown here in the equation 15. So whatever that I discussed so far, I put it in a table. And in addition to those parameters, we also define K3 and K4. We call it material correction factor. That would technically give the designer and the manufacturer the advantage that if you know more about your material, you can have a better prediction. You could modify based on the model of elasticity, or you could run these experiments, you find your best correction factor, then have a better prediction. Again, these tables, those models, they are all discussed in the papers that are cited here. Now, let's look at some data. There are a lot of information on the board. So I want to pause and make sure that everybody is familiar with the legends. So what I'm presenting here, we are looking at the measured data, we are looking at the prediction of our model, we are looking at the current AASHTO LRFD and some European models. The AASHTO LRFD model is shown with the dark blue line, which I hope is okay, clear there. And the data points are shown with the red dots connected with the green lines, and the predictive models are shown with the black dashed lines and black dot lines. The first important conclusion that we get is the AASHTO LRFD is not going to be able to predict the creep behavior of UHPC is far below the measured data. And the predictive model that we proposed has a reasonable agreement between the measured data, even though there are some cases that the model overestimates or may underestimate, but on average, it has a reasonable good agreement with the measured data. And the French model is also shown with the orange shaded area. So technically the French model, they have provided several factors and they have a range of numbers that you could go with a lower bound or upper bound. And so the advantage is the designer has the options to select different numbers. But the challenge is finding the correct correction factor is always tricky. There are some UHPC class materials that the measured data it's outside the predicted range, and there are some that are within the range. Here is the data, similar class materials, but the previous data were loaded at the early age. These ones are at the mature age when they had 20 KSI. Again, similar conclusions. The AASHTO LRFD is not going to be able to accurately estimate the ultimate creep. Our predictive model, even though in some cases it's underestimating, but on average has a reasonable agreement with the measured data. And in generally the European models, we look at the Swiss model and French model, they generally aligned with the predictions and with the material behavior. More discussions about these plots, the data, the comparison between the models are presented in the papers. Now, let's look at the shrinkage. So we followed the AASHTO thought process to estimate the shrinkage. We called the correction factors from those that previously developed for creep. And we also look at whatever that is written in AASHTO for conventional concrete. So again, for shrinkage, similar conclusions. The AASHTO model, the current version is not able to accurately estimate the shrinkage. The model that we developed, in general, on average, has an acceptable agreement, even though there are some cases that is underestimates or overestimates. However, with the correction factor, with the material correction factor that we are proposing, the manufacturers, if they know more about their material, they can find their own correction factors and it can be better predicted. The procedure, how to determine those, it's written in the paper. I'm not going to go in details how to develop it. Now, here are some concluding remarks. The current AASHTO is not able to calculate accurately predict the shrinkage and creep. The model that the procedure that we followed is based on the framework of the AASHTO, and we achieved the reasonable agreement between the measured data. Now, I'm going to quickly go through the model verifications with large-scale testing. We cast several girders, 7 girders in New Jersey and Florida, and those girders, they had 0.7-inch strand diameter, highly stressed. And with the rating wire gauges in the mid-span, we measured the deformation over time. Now, let's look at some results. So in this table, I'm looking at the pre-stress losses, the measured pre-stress losses, and those that I'm reporting is the last measurement that we were able to take before we test the girder. The measurements include elastic deformations, creep, shrinkage, and strand relaxations. So the measured between these girders, we had the girder that the losses was 12.4, and it also we had some girders that the losses was 22.5%. And for the prediction model, there is a procedure explained in AASHTO. We followed that procedure. All we did, we upgraded the material behavior. We implemented the creep and shrinkage model, and then we evaluated the current model, how good it does in terms of predicting the losses. So based on that, we see some cases that the prediction loss is very close to the measure. The difference is small. We had some cases that it was a little bit large. Now, in this plot, I'm looking at the effective stress in the strands. So the red dot lines, the red dots, they are measured data over time. And each plot is for each girder, and we look at the black dashed lines is our prediction. Again, the model is reasonable in predicting the effective stress, and the point that I would like to make is, for instance, for P3 and P4 girder, we measure the losses until 250 days, 270 days. So the majority of the loss, again, happened in the less than 30 days. That's the data point that we have. So which is consistent with the measured data in the creep, that the majority of the loss, it happens at the early age, and the remaining, there are not much difference. Here are three main concluding remarks. The measured prestress losses of the girder, it was 12.4 to 22.5, so we can have a UHPC girder that the ultimate, that prestress loss was as low as 12.4%, and the AASHTO prestress loss, when the time-dependent properties is updated, is able to predict the prestress losses, and results show the reasonable good agreement between measured data and then predictions. For more information, if there are questions, Dr. Graybill is a team lead of this research program. Please approach to him. Of course, you can reach out to me as well. And we also have these references here. There are appendix in these papers that the measured data, everything is published, and we are open to hear from the community if we can improve the model, if there are things that we can do to enhance the performance of the predictions. With that, I thank you all. If there's any questions, I take it.